Problem number 1. Let's first look at Ampere's law, which we are going to need the closed loop integral of B dot dl. I'm not lucky with my pens, am I? This is a good one. Equals mu 0 times I through plus, and here comes the famous term by Maxwell, d dt integral of E dot dA. And this part, including the epsilon 0, is often called the displacement current. Essential is that you realize that this is a closed loop and that you must attach to that closed loop an open surface, and you have to do the calculation of this through that open surface and take the time derivative. Now, the problem is a very cute one. I have a very small closed loop and a huge balloon. This is the balloon. And there is an opening here. So it's really a closed loop and it is an open surface. And I have such a closed loop and an open surface here. My Japanese balloon. Let me first blow it up. Here you see it. You see here the opening. I have a pencil here. And you see you can go in here the opening. So this is that closed loop. And in this problem we're going to make this closed loop go to 0. I have in here a radioactive source, alpha particles coming out. Alpha particles are 2 protons and 2 neutrons. There goes these alpha particles. So there is a positive current flowing out uniformly in all directions. Positive charge, positive current. Q enclosed here becomes negative, and therefore the dq dt becomes a negative value, because if we start with a neutral radioactive source, then the source becomes increasingly more negative. Now, if we're going to close this gap, we can apply Gauss's law, which says that the closed surface integral of E dot dA equals Q enclosed divided by epsilon 0. If I make this loop 0, then this term becomes 0. And so what I have now is that 0 equals, forget the mu 0, I lose that on both sides, equals I through plus epsilon 0 times d dt times the integral of the electric flux through that open surface. Look now that this term here, which is a closed surface, and this term here, which is an open surface, become the same if you make the loop 0. And so I now find that 0 equals I through plus, I take the derivative, and so this becomes dq dt. I have an epsilon 0 here, an epsilon down 0 here, and so they cancel. And this is a totally trivial result. It is immediately obvious. What it's telling you is that I through this closed balloon equals minus dq dt. Well, we did not need Maxwell's equations to tell us that. The radioactive source is becoming more and more and more negative, so it's clear that the current that is going out through this surface, per definition, is the charge per unit time, and the minus sign is only because the radioactive source becomes more negative. The beauty, however, is that we find this absolutely trivial result, for which we did not need Maxwell's equations at all, but it is entirely consistent with Maxwell's equations. And it's only consistent with Maxwell's equations because we allowed for this displacement current term. If we didn't have this displacement current term, we would have found the embarrassing answer, clearly the wrong answer, that I through would be 0, which is obviously not true. And so what I like about this problem, that it derives in what you may call a rather complicated way, using Ampere's law, including the displacement term. It derives in a very complicated way an answer which we already knew, namely that the current is nothing but the charge per unit time. This we could have written down without thinking. We could only have found it from Maxwell's equations if, however, we had incorporated the displacement current. And that's why I really like this problem quite a bit. It's really a marvel in my opinion.